This video we will be discussing some of the basic properties of light as well as different light behaviors. So what is light? Light is an electromagnetic wave which radiates at various wavelengths, and an electromagnetic wave, or EM wave for short, simply consists of the oscillation of both electric field and magnetic field waves. And we will take a look at what this looks like exactly in the next slide. So here we have two images, but we'll focus on the left first. It's important to note that this image on the left is not an EM wave, so this is not what a light wave would look like. However, it is helpful to label a few important things. So for every wave, there will be an amplitude, which is simply the height of the extrema. We also have a wavelength, which spans one full period of the sinusoidal wave, and then finally the trough and the crest, which are the minimum and maximum points of your wave. So now we can take a look at this right image. So this is an EM wave, and it was a little bit closer to what a real light wave may look like. And as we can see, there are actually two sinusoidal waves occurring in a three-dimensional plane. We have the red, which is the electric field, and the blue, which is the magnetic field. And to emphasize the orientation of these waves, from this graphic we can see that the red electric field wave is oscillating in the ZY plane, while the blue magnetic field wave is actually oscillating in the XY plane. So the oscillations of these two waves are perpendicular to one another in a three-dimensional space. Here are just a few wave elements, most of them which we discussed in the previous slide, but some of the new ones are frequency, period, and phase velocity. So the frequency of a wave is going to be how many wavelengths pass through a given point over time, and this is in units of hertz. We then have period, which is simply the inverse of frequency. So this will be how much time it takes for one wavelength to pass a particular point, and this is typically done in seconds. Finally, we have phase velocity, which is the rate at which a wave propagates through a medium, and this is given in meters per second. Light follows a very interesting phenomenon known as the wave-particle duality, and this is the idea that all quantum entities may behave as both a wave and a particle, and this has actually been shown many times in real-life experiments, but here we have a very simple graphic of what this looks like. So if we take a look at the left, here is a demonstration of wave behavior. So simply put, we have these red waves passing through two slits at a boundary, and as they pass through, these waves bend into an arc, forming multiple bright spots on the back plane. This is a little bit different of what we would expect since there are only two slits. However, these multiple bright spots can be justified by constructive interference and the bending of these waves, which we will discuss in more detail later on in this video. On the right, we have a more intuitive image of the particle behavior. So here we have a group of particles approaching the same boundary with the same two slits, and as expected on the right plane, we have two bright spots. It's helpful to be familiar with the electromagnetic spectrum, or the EMS, and the EMS is a range scaled by wavelength or frequency over which radiation exists. And different types of radiation close in proximity to each other on the EMS have similar properties and characteristics. Just to highlight some simple trends in the EMS spectrum, going from left to right, we have the highest energy to lowest energy. This is also going to correspond to the highest frequency to the lowest frequency. Now, the reason why the highest energy and highest frequency line up together is because higher frequencies mean more oscillations within a given amount of time, which means more kinetic energy carried by those waves. And then finally, again from left to right, we have shortest wavelength to longest wavelength. Now that we discussed some basic properties of light, it's time to talk about light behavior. There are several standard light behaviors which are critical to understand in order to create a functional optical system, and these behaviors include reflection, refraction, dispersion, interference, and diffraction. Reflection is the redirection of light rays when encountered by an interacting surface, and reflection will always follow the law of reflection, which simply states that when rays are reflected, the angle of reflection is equal to the angle of incidence, or theta I equals theta R. We can take a look at a demonstration of this in the image down below. So we have a red light coming and reflecting off of this reflective surface, and as we can see, the incident angle is the same as the reflective angle. Now there's this dashed line right here, that is called the normal line, and the normal line is present in every reflection, and it divides the incident and reflected angles symmetrically. Light can also reflect off of a curved surface, and it will still follow the law of reflection. So here we have two examples of a curved mirror. We have a concave and a convex. So if we take a look at the reflected rays in the blue, we can see that if we were to draw the normal line, it would follow a path following my red laser pointer here, as we need to divide this full angle into two equal parts. And we can do the same thing for the convex mirror. So if we are simply visualizing this incident ray with the reflected ray, we can assume that the normal line will follow some sort of path, as so to divide that full angle into two equal parts. A few highlights of the concave and convex mirror. As we can see from the image, the concave mirror will have the reflective surface on the inner side of the curve, while the convex mirror will have the reflective surface on the outside of the curve. A quick comparison of the convex versus concave mirrors. A concave mirror is having light shown towards the inside of the curve with a positive focal length, and real images are formed. So some applications of this are magnifying, makeup mirrors, reflective telescopes, and torch lights. Meanwhile, a convex mirror has light shown towards the outside of the curve, and these will have a negative focal length. And instead of a real image, a virtual image is formed, and some applications include side view or rear view mirrors and street mirrors. We'll go into more discussion about real image and virtual image when we discuss ray tracing later on in the course, but to briefly give you an idea of the difference between the two, the real image is going to be formed by the actual rays converging to a point, while the virtual image is going to be formed by rays which appear to be converging at a point. But again, we will revisit that idea later on in the course. Alright, next we can talk about refraction. Refraction is the redirection of light rays when traveling through a medium, and this behavior is highly dependent on the refractive index, or n, which is a dimensionless value dictating how fast or slow light will travel through a given medium. And the value for n for any material can be calculated by c over v, where c is the speed of light and v is the phase velocity. Refraction is going to follow Snell's law, or the law of refraction, and this is a demonstration of the relationship between the refractive index and the angle which rays will make to the normal line in different mediums. So the equation for this is n1 sine theta 1 equals n2 sine theta 2, and the subscripts 1 and 2 are referring to the medium first traveled by the ray, and the subscript 2 is the medium which the ray travels in last. So if we take a look at the pictures down below, we can see that we have a green ray passing through medium 1 with n1 making an angle of theta 1, and as it crosses that boundary, it is now entering a medium of n2, creating a new angle of theta 2. So this can be demonstrated in real life with this pencil experiment. So if a pencil is placed in water, our eyes see that it looks like it's bent, but this is actually due to refraction. So as we can see, the pencil traveling through the water will not have the same refractive index as air. So as the pencil travels through the water and then travels through the air next, they will have different angles with respect to the normal line, making the pencil appear to be broken. It can be easy to confuse reflection and refraction sometimes, so here is just a quick comparison of the two. The reflection is going to be the symmetrical redirection of rays when encountered by an interacting surface, while refraction is the redirection of rays when traveling through mediums with various refractive indices. Total internal reflection is when a ray is reflected completely back into a medium by a separate surrounding medium with a lower refractive index. So it's important to note this can only happen if the second medium has a lower refractive index, not if it is a higher one. And the critical angle is the incident angle at which the refracted ray forms a 90-degree angle with the normal. So if we take a look at the image down below, the total internal reflection is demonstrated by this blue line. So as we can see, the blue line approaches the normal, but because of this incident angle, which is a specific value for this case, instead of coming out into the air, it will actually be reflected immediately back into the glass. And then the critical angle we can see through this red ray. So at this particular incident angle for these two particular medium, the ray will be perpendicular to the normal line instead of coming out into the second medium. And then finally, this green ray is just demonstrating a simple refraction. Dispersion is the phenomena that the refractive index of a medium is dependent on the wavelength of a passing light ray. So this can be demonstrated through shining white light through a prism. When we do this, we can see the multiple colors of the white light being separated, and this is due to each of those wavelengths traveling through the prism at a different time interval. Next, we have two different types of interference. So waves can undergo constructive interference or destructive interference. Constructive interference is when two or more waves collide in phase with one another to create a resultant wave of larger amplitude. So a few examples of this are pushing a child on a swing, and in this case the push and the swing are both considered waves and they're moving in the same direction, or in other words, they are in phase with one another. Destructive interference, on the other hand, are when two or more waves collide out of phase and create a resultant wave of smaller amplitude. So a good example of this is noise-canceling headphones. Here we can visualize what constructive interference and destructive interference look like. So in these two images, the dark purple line is the resultant wave for the constructive interference, and the dark orange line is the resultant wave for the destructive interference, and those faded lines are going to be the two component waves which are combining. So as we can see in the constructive interference, the peaks and the troughs of the light blue and light red lines align, making the resultant amplitude much larger, whereas in the destructive case, we see that the peaks and the troughs are misaligned between the light red and the light yellow waves, causing the resultant amplitude to be much smaller. Diffraction is another unique light behavior, and this can be demonstrated through something called a single slit experiment. So in the single slit experiment, monochromatic light is shown through a narrow slit, and the light intensity is demonstrated here in orange. So if we analyze this graphic, we have the red waves passing through just a single slit at a boundary, causing them to bend. And the way that it was discovered that these ones were bending around was by measuring the different light intensity on some backplane. and it was found that the intensity at the center was the greatest, and the intensity slowly begins to fade off towards the edges of that arc. So again, this single slit experiment was a very good indicator of light behaving with diffraction. And diffraction is the wave-like ability of light which allows it to spread out when passing through a narrow slit or bend around corners. And diffraction is often accompanied by wave interference. Here's just a quick table of the summary of light behaviors. You can feel free to pause the video here and review all of these terms and their definitions if you would like.